Okay, so let's start on this test review. So we're going to have an inclined plane here, and we'll have a box, mass M, and say a pulley, and so this mass M is connected with another box of mass M as it pulls up an inclined plane. This is an angle theta, and so one of the techniques we need to use in order to solve this problem is we need to draw some free body diagrams. So free body diagram 1 for mass M is we'll have M here, and we'll have the weight going down, and then we can break this down into its components. This is going to be theta here, so this is going to be adjacent, so this is going to be equal to mg cosine theta, and this one will be mg sine theta. So next up, what we can do is we can go ahead and draw the normal force, and we also have to have a coefficient of friction on the ramp, and so then there's going to be a kinetic friction force here. So next up, what we can do is do the free body diagram for this one, and we're also forgetting the tension here in the rope. So we're going to have W here and T pointing up here. So the T's are going to be equal to each other, and so this is basically how you set up this problem. So we can go through the motions and finish this. So for the forces in this direction, we're going to have F net is equal to MA, which is going to be equal to we're going to have FK, we're going to have T, we're going to have the frictional force, we got that T, and mg sine theta. So those are the three forces on that side, and we can solve for T. T is just going to be equal to W in this case, which is going to be capital Mg. And so T in this direction is going to pull this way, and so then this is going to be the opposite of the other two forces. And so then we can solve for the acceleration here, and just say that A is going to be equal to mu of k mg cosine theta minus big MG plus mg sine theta. So next up, let's do another problem. And if we go ahead and do a problem with uniform circular motion, and we should describe, so say we're spinning a ball vertically or horizontally around our head. So this is our hand here. And we say that this ball has some Vt. And for this case, when we're spinning it horizontally, the angle theta is not going to matter, because this angle theta won't matter at any angle, because mg or W will always be pointing down of the weight, but it's going to be different if we're spinning it vertically. So why don't we analyze both cases, and then we'll go back to solving this problem. So if we go ahead and analyze the vertical case, when we're at some angle theta here. So what ends up happening is at the very bottom right, we have mg fully, and F radial here, pointing inwards, due to F radial being mvt squared over r. But mg now over here at the angle theta is pointing in this direction, and so this force here, in order to account for them being lined up, has an angle theta, and so we'll have to draw a triangle here and use our trigonometric identities to find what the force is there. So going back to our case here, all we have to do up top is when it's spinning horizontally, the angle theta doesn't matter, and so then our force here is just going to be F radial is going to be equal to mvt squared over r. And so then this becomes a really easy problem to solve. Another thing you should do is go back and look at your labs for chapter 5 and do the free body diagrams for those again. That should help out a lot. And I would also do conceptual questions involving that one as well, just to make sure you have all your ducks in a row. Go ahead and look at the kinetic energy and work video and how the work energy theorem can apply. So say we have a force that is divvied up into its components. You can do this in any case where you have one force. You can split it into its, if you have a force here, you can split it into its I hat and j hat components, and given some angle theta. And so then remember that work is equal to our force times our distance. So this is not going to be, you're not going to multiply, if you're breaking down this into components and you have Fy and Fx, you're multiplying it by, you're going to have some distance d, right, but you'll have to split d into its components as well. So this will be Fyy and Fxx. And then from there, you can add those up, and that will yield an answer there. So just remember that when you're splitting this into components, these two add up to give you the total work. We talked about in my one video how in my one recitation where we did a spring, and we talked about how we compressed it a certain amount, and we were able to go ahead and derive how far it went up a ramp with respect to how much the spring was compressed. So so I would go and revisit that video. I would go ahead and just remember that our power formula here is just going to be equal to work over time. That should be on your equation sheet, and you can dole that out whenever you need to find power. Free body diagrams, just remember how to do those. You guys should be pretty good at those by now. Another problem that we did is we had the ramp right with some angle theta, but if you know what the height is of the ramp and the ramp is frictionless, we can use energy instead of knowing what the actual angle theta is. We don't actually need this because we can just use mgh equals 1/2 mv squared to find the velocity at the bottom of the ramp here. So if we were to go ahead and revisit some energy problems here, if we go ahead and talk about, so say we have a ball, right, in uniform circular motion at some angle theta, and this has some initial velocity v, and at the bottom we have some velocity v. What we can do is we can use energy in this case to go ahead and solve for, this is L. We can go ahead and solve for what this what angle theta this is given any of the other parameters. So you can say at the beginning we have 1/2 mv naught squared, and at this point we'll have some angle theta, so plus mgh, where h is the height difference between the bottom and the point at which you're kicking the ball or giving the ball that initial velocity, and then at the very bottom it's going to have 1/2 mv squared. And so you can do a couple things here. What you can do is you can solve for what h is geometrically. So in this case we have a circle, right, and an angle theta, and we said that this is h, right, and this is an arc length. So this is not actually a triangle, or even a right triangle for that matter. And so what we can do is we can say, all right, well, we need to find what h is. And so what we can do is we can say, we can draw a little line here to make this a right triangle. And what we can do is, using theta and what L is, we can say, well, this part here is going to be L minus h, and this part here is h. And so using what L is and what theta is, we can go ahead and find what the quantity L over L minus h is, and then we can solve that for h. And so from there, what we can do is we can solve for what h is in terms of trigonomic functions and L. So in this case, this is going to be the adjacent here. So this is going to be cosine theta L minus h all over L. And so then we can say that theta in this case, or we can solve for h or theta. So either way, we can end up solving this problem. And again, this is cosine theta is equal to L minus h over L. And so then h is just going to be equal to L1 plus or minus cosine of theta, because we multiply L to the other side and then we subtract L, but then we take the negative to get positive h. And so then it yields this instead. And so what we can do is we can go ahead and we can plug this into our equation here and then solve for theta. So let's do that. So we're going to have MGH, but then we can erase that and plug in L there times 1 minus cosine theta. And from here, what we can do is we can say, all right, well, this is going to be equal to 1/2 mv squared minus v naught squared. So I just subtracted this to the other side and factored out the m over 2. And then, so we can easily see now that the m's cancel, and we can start solving for this. So get rid of the m's, and we can take g and l to the other side, so we get 1 minus cosine theta here is going to be equal to 1 over 2gl v squared minus v naught squared. And so then we can solve this for theta. And to do that, we just got to do some algebra. And so now this is going to be negative. I'm going to put a negative on the other side. So we're going to have cosine theta is equal to negative 1 over 2gl v squared minus v naught squared. And then we'll have minus 1. And so we distribute that, and we'll take the arc cosine of both sides. So we have theta is equal to arc cosine of 1 minus v naught squared all over 2gl. And that should go ahead and yield you your angle theta here. So you can solve for this angle theta at any point. There is a quicker way to do this because you have what L is, and you can just instantly solve for what L is. But if we want to use all the variables that are given to us, we can go ahead and do this as well. So you can solve for theta at any single point with respect to these variables here. Go over which forces do work, and how and we talked about how potential energy is stored. There should be a basic momentum problem. Remember how to use your impulse formula. This one's really simple. This just decomposes to m2v, and these m's are the same. And just take great care with your directions here. And then remember how to use, remember the difference between the types of collisions and what that means for the problem in terms of conservation. And then go ahead and do that last homework problem on your homework assignment a couple times in order to get practice with talking about conservation of momentum, but with conservation of energy stacked on top of it. Okay, good luck on your test today, guys. I wish you guys luck. This should be an easy, quick video to watch.